Welcome to the Triple Physics Paper 2 Space Physics revision presentation. First thing we need to know is all the things that our solar system is made out of. The solar system is really our sun and everything that is in orbit around it. So that's the star in the center of our solar system, the sun, the 8 planets that orbit around it, but also the asteroids, the comets, the dwarf planets, and also all the moons that orbit the planets in the solar system. They all form part of our solar system. The solar system is just one little solar system with one star in it, which forms part of the Milky Way galaxy. The Milky Way galaxy has hundreds of billions of stars in it, a lot of which have their own planets orbiting around them. Our solar system, just like any other solar system, was formed from a big cloud of dust and gas called a nebula, and the force of gravity pulls that cloud inwards, pulls it in tighter and tighter, and the sun forms at the center of that cloud of gas as it's pulled together. When the sun started shining, the energy from that pushed a lot of the lighter gassy material in the cloud out to the edge of the solar system and left behind all the heavier, rockier stuff closer to the sun. The sun started shining because as gravity pulled all that gas and dust tighter and tighter together, the pressure and temperature at the center of it started making that cloud hotter and hotter and hotter until the temperature and pressure were high enough for the nuclei in the center of that to start fusing. Nuclear fusion started, and that's why the sun or any star starts shining when nuclear fusion starts in the center of it. And we start doing fusion, sticking hydrogen nuclei together to make helium nuclei. So this stage of a star's life is called its main sequence. When fusion starts, the forces in the star are balanced, gravity pulling everything inwards tighter and tighter, but the pressure from the fusion inside of the star pushing outwards. Those forces are balanced, and the star stays in this main sequence for millions or even billions of years, depending on how much hydrogen there is in it to keep doing fusion with. When the star runs out of hydrogen to do fusion with, it starts entering the end of its life cycle. And what happens next depends on the mass of the star. A small star like our sun keeps doing fusion with the nuclei that are in the star, putting together heavier and heavier nuclei until nuclei all the way up to iron are made. As it's doing this, the star is cooling and expanding, and the star that's made is called a red giant star. Once fusion stops in the center of that star, those outer layers of the star just drift away to leave behind the old core of the star called a white dwarf star. And when that star stops shining and runs out of energy, what's left behind is a black dwarf. So a small star becomes a red giant, then a white dwarf, and then eventually ends up as a black dwarf. A much larger star keeps doing fusion after the hydrogen has run out, making heavier and heavier elements all the way up to iron, and again expands and cools. But the size of these stars mean we now call them a red supergiant star. When fusion stops in those stars, the pressure is still so great in the middle that it collapses and explodes in a massive explosion called a supernova. The bit of star left behind after a supernova is either a neutron star or a black hole. Now, it's in the supernova explosion that the forces are big enough to stick together the nuclei of atoms to make elements heavier than. So fusion is sticking together smaller nuclei of elements to make larger ones, and all the elements apart from hydrogen and helium have been made in stars through the history of the universe, and they've then been spread throughout the whole universe as those stars explode in big supernova explosions. So that means that all the atoms we see spread through the universe that are heavier than hydrogen and helium were made in stars and then spread through the universe by exploding stars. We're all made of atoms that came from exploding stars. When we then look at how things orbit and move around in our solar system, we call anything that's orbiting another object because of its gravity, we call it a satellite. Now, of course, there are natural satellites like the moon around the Earth or moons around other planets in the solar system, but there are artificial satellites as well, things that humans have launched, for example, weather satellites, the International Space Station, and any other probes we've launched into orbit around other planets. Satellites orbiting around objects because of their gravity is a good example of something doing circular motion. Circular motion means that the object really wants to fly off in a certain direction. You see the blue line on the diagram here. If there was no gravity pulling a satellite in, it would just fly off in a nice straight line. But the force of gravity, there's our green arrow there, keeps pulling it towards the Earth, so its direction keeps changing, so it moves in a circle. So instead of flying off in a straight line, it moves in a circular path around the Earth. Its direction keeps changing. Although it's moving at the same speed, its direction keeps changing. Now, this means that we can say that its velocity is changing, because velocity is speed in a certain direction. If your direction keeps changing, then your velocity is changing. If your velocity is changing, you are accelerating. Acceleration is a change in velocity. Now that's why we can say that a satellite orbiting around the Earth or anything else at a constant speed is still accelerating. Its direction keeps changing, which means its velocity is changing. And if your velocity is changing, you are accelerating. When we look at the light coming from different things in space, then it's important we think about the wavelength of light coming from them. Red light has the longest wavelength of the visible light we can see coming off objects. Now, when scientists look at the light coming from galaxies far, far away from us in the universe, they know what wavelength of light should come off them. But when we look at the wavelength, we find the wavelength of light is longer than we expected. It's redder. We call it red shift. The wavelength of the light, which should show this pattern here, these frequencies of light have increased. They've moved down towards the red end of the spectrum. Now, why is this happening? Well, it turns out redshift is happening because the wavelength is getting longer because those galaxies are moving away from us very fast. The galaxy moving away from us very fast stretches the wavelengths of light coming from it, which make them look redder to us. Now, the faster the galaxy is moving away from us, the more those wavelengths get stretched, or the greater the increase in wavelength. Scientists have been looking at distant galaxies for a long time, looking at the wavelength of light coming from them, and all galaxies we look at show red shift. They all show they're moving away from us. So in other words, everything in the universe is moving apart, moving away. So the whole universe is expanding. Red shift shows all the galaxies moving apart, so the whole universe is expanding. Now that means if it's expanding, it must have started out much smaller a long time ago, and it's been expanding. We call this idea the Big Bang Theory. The idea that the universe started off much, much smaller, much, much hotter, much, much denser, and then expanded. And it's been expanding ever since. We can see that expansion with the red shift, the increase in the wavelength of light coming from the galaxies we look at. Now, scientists expected that as the universe expanded, it would get slower and slower as it expanded until eventually it stopped. But recently, now that scientists have looked at a lot of the galaxies, they've actually noticed that the universe is accelerating and expanding at an even greater rate. Now, we don't have the perfect idea to explain that at the minute, and scientists are looking at new ideas like dark matter and dark energy to explain why the universe is expanding at a faster and faster rate. That's a good example of scientists having to change their theories to fit new evidence. At the minute, the Big Bang Theory is the best explanation of all the evidence that scientists have gathered over the years. But every time we get new evidence, we change our theories. So if when you've got a theory and you do an experiment and the evidence doesn't match it, you have to go back and change your theory to match up with your new evidence.